Here's a relatively straightforward fluid mechanics problem which actually combines the ideas of mass conservation, energy conservation, or Bernoulli's theorem, and momentum conservation. So this actually touches upon all three topics. And this is the kind of question that you might see usually as a first year undergraduate student if you're doing some sort of engineering. And if you'd like to see anything similar to this on the channel, let me know down in the comments. So in this question, we're basically dealing with a dam, and there is, or as the question calls it, a spillway. So we're dealing with this spillway flow, and the flow is assumed to be uniform and hydrostatic. So basically, we're dealing with a flow that, hydrostatic basically means that the velocity here is the same as the velocity here, and is the same as the velocity here, for instance. So we don't really look at how the streamlines change in terms of speed just before the dam. Instead of that, we just look at sort of like the overall effect, which is we're looking at the speed here and here. And then we have to find out two things. So this question has two parts. The first part is finding V2, and the second part is finding the force per unit width of the water on the spillway. So this is the force acting from the water on the spillway. Okay, let me remove some of the drawing, and then for part A, I would first start by looking at mass conservation, right? So we have m in, so mass flow rate in is the same as mass flow rate out, and then I would draw the control volume. So the control volume in this case would be this right here. So it goes along this surface and it cuts through the left and the right sides, and that's it. So you essentially have two places. You have one inlet and one outlet, right? So you have this here is the inlet, like this whole vertical surface is the inlet, and this is the outlet, right? There's no water that leaves the surface through here because the surface of the control volume in this area is tangent to the velocity of the water. So the equation for mass flow rate in isn't anything too difficult, so that's just density times the area. Now the area is essentially this height of 5 meters times the width, but the width is the same for the inlet and the outlet, but we'll write it down and then you'll see that it actually cancels out. So the area is 5 multiplied by the width, because basically what happens is you have a height of 5 meters like this, and you have an unknown width, right? And this actually forms a rectangle. So this has, again, this has a height of 5 meters this way, and then the velocity of the water is going through this rectangle. So that's what I would call the inlet area in this question. So that's the area, that's the density, and then we have our unknown velocity v1. And the mass flow rate out is going to be having a similar expression. So it's rho, and then you have 0.7 W times v2, like this. And yeah, that's basically what we have. So we can cancel out the rows, and then we can say that we can also cancel out the W's as well. So we have 5v1 is equal to 0.7 times v2. And actually what I'm tempted to do is I just want to keep symbols for now. So this 5 that I wrote here, this is essentially my h1 and this is my h2. So I'm gonna keep them as h1 and h2. So this is h1 v1 is going to be equal to h2 v2, which means that I can express v1 in terms of v2. So v1 is going to be v2, and then we have h2 over h1, and that's it in terms of V1. So we don't actually we can't find V1 and V2 because we have two unknowns in one equation. So the other thing that we can use is Bernoulli. So we apply Bernoulli's theorem in the following way. So we're gonna look at the surface of the water, let's say somewhere at this point, and we're gonna follow this streamline that goes all the way to here, and we're gonna apply Bernoulli's theorem. So this is point 1, this is point 2, and we know that at point 1 we have atmospheric pressure, so that's our static pressure, plus, and then we have 1/2 rho V1 squared, and then plus rho G. So we have rho GZ1. So if we're using the bottom as the reference point, so this is basically my Z equals 0. This is my reference point, or my reference line. Then this term becomes just rho GH1. And on the other side, so for point 2, we have atmospheric pressure again, because we're looking at the water surface, and then dynamic pressure 1/2 rho V2 squared plus rho GH2. So we can cancel out the atmospheric pressures, and then we can rearrange. So remember, we're trying to find out V2. So I'm gonna say that 1/2 rho, so V1 squared is this. So that's V2 squared, and then H2 squared over H1 squared plus, or actually, let's try this. I'm gonna bring this to the left side. So this is minus 1/2 rho V2 squared, and that's rho G, and then we have H2 minus H1, like that. And if you think about it for a second, this term is actually negative because H2 is smaller than H1. So what I'll do instead is I'll multiply everything by -1, and when I do that, I'm gonna switch the signs of everything like this. So we have 1/2 rho V2 squared times 1 minus, and then we have H2 squared over H1 squared, and that's rho G H1 minus H2. Of course, we can cancel out the densities like that, and this becomes V2 squared over 2, and then we have H1 squared minus H2 squared over H1 squared is G H1 minus H2. And if you look at this closely, you'll realize that there's another cancellation that we can do. So we've got V2 squared over 2, and this is a difference of squares, so it's H1 minus H2 times H1 plus H2 over H1 squared, and that's G H1 minus H2. You can cancel out those, and we should end up with V2 squared is 2G H1 squared over H1 plus H2. And that's the expression for it. And now we take the square root. So V2 is just H1 square root of 2G H1 plus H2. And if we put the numbers in, I think this will come out as 9.3 or something. So H was 5, I believe. I'm going to take G as 10. So we have 5 plus 0.7, so that's 5.7. And this should give us, so 20 divided by 5.7 squared times 5. So it's about 9.36 meters per second. And that's part A. Now for part B is asking us to find this force. So for this force, what I would do is I would find V1. So V1 is first going to equal V2 times H2 over H1. So that is 9.36 times 0.7 over 5. And we expect V1 to be less because it's going through a higher surface area. So that is approximately 1.31 meters per second. And that's it. So that's the value of V1. And then we have to find this force, essentially, that's acting in this on this control volume. So the control volume, it was this kind of like purple, the control volume is surrounded by this purple surface, and that's what we call the control surface. And then we have to kind of draw that separately and see what forces are acting on it and what other forces are going through it as well. So we've got something like this. There is one inlet on the left hand side, which means that, as you know, the water is going in through here. So this is this velocity is going to be V1, and then we have another velocity here, which is V2. So those are things that we did in part A, basically. And then we've got the spillway being somewhere here, like this. And there's a force acting on the spillway by the water, but you can also flip the logic and say that the spillway is acting with the force on the water. And we don't really know much about the force yet, but I'm just going to say that the force on the water is going to be acting in this way, by the spillway. Now, in addition to that, the question tells us something interesting, which is that the flow is assumed to be hydrostatic, which means that if the flow is assumed to be hydrostatic, we have to take into account the fact that there is a pressure, or there's a force, due to hydrostatic pressure acting on this side, and that force is going to be acting this way, right? So we have a force like this. So this is the pressure distribution, right? So you know it's a linear pressure distribution from top to bottom, and then we have the same situation here. So we have this kind of pressure distribution on the right hand side. We know the height, and essentially we know that the force acting on a vertical wall, so this is h1, or I think we use lowercase h1 and lowercase h2. So the force due to the pressure acting on one is the area of that light blue triangle, which is essentially base times height over 2, right? So the base is rho g h1, the height is h1. You multiply that by the width, which is in the screen. So that's 1/2 rho g h1 times h1 again, so that's squared, multiplied by the width. And the same happens at the outlet. So this is 1/2 rho g h2 squared times w. So there are actually three forces that we're dealing with, right? There's Fp1, there's Fp2, and then there's this unknown force that we're trying to find. So let's write the equation of momentum conservation, because that is the equation which contains information about the forces. So we have that the net force is equal to the momentum flow rate out minus momentum flow rate in. And let's see what we have. So in terms of the net force, we've got three forces. Two of them are to the right. So that is F and Fp1. So we have Fp1 as 1/2 rho g h1 squared w, and then plus F, and then minus 1/2 rho g h2 squared w. And that's equal to the momentum out. So the momentum out, we know that's the mass flow rate, which is the same at both stations because mass is conserved, multiplied by V2 minus the mass flow rate multiplied by V1. And that's it. Now we just have to rearrange this, manipulate it in a few ways so that we can extract what F is in the end. So let's do that. Let's write that F is equal to, so I'll keep F on the left and I'll throw everything on the right. So that's m dot and then V2 minus V1. And then we've got plus, so we switch the signs of those terms basically. So we've got 1/2 rho g, and then we have h2 squared w minus 1/2 rho g h1 squared w. Now remember, the question is actually asking us to find the force per unit width. So yeah, we have to find the force per unit width. So at some point we're gonna have to divide this entire equality that we have here by this w, because we don't know the w, we just want the force per unit width. So we've got the force, and then we have the mass flow rate. So the mass flow rate is density multiplied by, you can take whichever station you want. I'll take number 1, for example. So this is going to be h1w, so that's the area, that's the area of the rectangle as we discussed earlier, multiplied by v1, and that's v2 minus v1, and then 1/2 rho gw, and then we can factorize this like that. And now we can divide by w to get that force per unit width. So this is what the question wants, F over W. So when you do that, you have a W here that gets cancelled, you have a W here that gets cancelled, and you're going to end up with rho H1 V1 and then V2 minus V1 plus 1/2 rho G and then H2 squared minus H1 squared, like this. Okay, so now we just have to put numbers in. So F over W is going to be equal to density, which is 1000, H1, which was 5, and then V1, which came out as 1.31. Then we have V2 minus V1. So V2 minus V1 was 9.36 minus 1.31. And then we have this second term, which if you look at it closely, you'll realize it's negative. Right, so you have 1/2, and then you have 1000, then you have 10, and then you have that difference in squares of the height. So you have, I'll put square brackets. So H2 was 0.7 squared, H1 is 5 squared, so you see that this will become negative basically. Therefore, the force per unit width will be equal to, so now this is just a calculator exercise more than anything. So we've got 9.36 minus 1.31, so that's 52,727.5, and then I'm gonna put minus, and then we have, I'll multiply those as well. So 0.5 times 1000 times 10, and then times basically 25 minus 0.49. This is minus 122,550. Pretty big numbers. And finally, we're gonna get 52,727.5. So the answer is gonna be negative, and it's gonna be 69,822.5. Remember, those are not newtons, because this is a force per width. This is newtons. Those are newtons per meter, and it's negative. Which means that because it's negative, it basically means that the force acting on the water, on the control volume, so I should probably write it with words here. So this means that the force acting on the CV, in other words, on the water itself, is acting to the left. So the water is basically experiencing a force to the left due to that dam, due to the spillway, right? Which means that actually the spillway experiences a force to the right because Newton's third law, right? So the spillway will experience a force this way, which is exerted by the water, and the value of that force is going to be 69,822.5 newtons per meter. So I should say force per width, not force, but yeah, you get the idea. So that's how this problem works, and that's the end of it.